So what I plan to do, because this is a big audience, I thought I wanted to have another prepared talk, because otherwise if I improvise with and draw figures on the whiteboard, it's probably not even very hard to see for those in the back of the room. So I wanted to talk with slides. So I thought about talking about Scala, the simple parts, which was a talk I have given earlier this year in the month of June in a number of conferences. And also it's because it's a talk I care deeply about, because I care deeply about the simplicity and that might look like a strange thing to say, because I think Scala has been criticized a lot for being complicated, and it seems complicated, and we can talk maybe in the question time or afterwards for some of the reasons why it's complicated or why it might look complicated. I think part of the reason is that it's very new. In particular, for many people, the functional part is something very strange, and everything which is very new at first looks complicated until you figure out what it is and what the principles are, and then sometimes it's simple and sometimes it stays complicated. So what I hope to show you is that if you take the right approach to Scala, then it can actually be a very, very simple language, and that the simple parts are the parts sort of worth looking at in Scala and worth concentrating on. Okay, so let's get started. So 10 years of Scala, I already talked about that yesterday, so I'll skip that. So in 10 years, our user community has grown up a lot. So we have now, I think, probably more than 100,000 developers. That's probably professional developers. I think if you add the hobbyists, we have many more, several hundred thousands, I would say. Another harder number is the Coursera course on functional programming and the one on reactive programming together had more than 200,000 enrollments. Of course, some people enrolled in both courses. Some people might have enrolled several times in the functional programming course, so we can't really count how many people that is, but it is a lot. It is a lot of people enrolled in these courses. If you look at the RedMonk programming language rankings, which to my mind are the most solid ones, because they don't just count words that you find on the internet, but they count essentially the projects on GitHub and the questions on Stack Overflow, so essentially solid things that developers do. Then on GitHub in these language rankings, Scala is about number 13, so it's not a top 10 language, but it is solidly a top 20 language. And of course, what matters much more than these numbers is that we see it here, and I see it in lots of places where I go. There are many, many, many happy users and successful rollouts, and that's the important thing. Good, so that's the great part of the success story. So should I finish here? Well, no. Actually, what I also observed is that Scala is also being discussed more controversially than usual for a language at its state of adoption. Seems everybody has an opinion about it, positive or negative, but Scala seems to be a language that incites strong opinions in people. So why is that? Well, the controversies, in fact, are both internal controversies and external ones. So the internal controversies are that often you have a situation that different communities or different people don't really agree what programming in Scala should be like. Part of the problem is that Scala is very new, like I already said, so a lot of people are feeling their way. And the other part of the problem is that Scala is a very general language, so it attracts people from very different communities. It attracts people from Java, a lot of them come from Java. It also attracts people from dynamic languages like Ruby, and it attracts people from essentially classical, statically typed functional languages like Haskell. And these three communities, I think, have never before mixed so much, and Scala in some cases is becoming their battleground, that every community says, you have to do it this way, and the other community says, no, you're talking nonsense. So that's the internal controversies that we have. Oops. Then you hear also external complaints, and they come from all sides, really. What I used to hear a lot is Scala is too academic. A lot of people have said that. It's an academic language. What I hear more and more is Scala has sold out to industry. In particular, the recent events, a lot of that came from that side. A lot of people say Scala's types are too hard, and others say, well, no, Scala types are not strict enough. We need more types. And a lot of people say Scala is everything and the kitchen sink. So everything is in this language, which in fact, that's the one that sort of gets me most upset, because it's not true. It's absolutely not true. Scala is a language with a fairly modest number of concepts. You can't compare it with, let's say, Lisp, because it has a type system, and types add complexity, of course. But if you compare it to other statically typed languages like Java or like Haskell, the closest one, then it is, in terms of feature count, on the same level. So if you look at how many features, how big is the compiler, how long is the spec, how large is the grammar, everything you look for is about the same. And if I give you some languages that are not about the same, if you look at C#, then in all measures of C# is about 4 times as large as Scala, 4 times. F#, 2 to 3 times as large. C++, we don't even talk about that, 10 times as large. So by objective measures, it's not that large, but it feels large, again, because it's very general and people do lots of different things with it, and they look weird to some parts of the community. I think that's part of the problem. Okay, so I think the challenge that we have here in this niche in the language space is that to get people forward and to get people to agree, we have to make clear what the essence in programming in Scala should be. And with all the different voices, sometimes that gets lost a little bit. And it's very hard to come up, and I can't give you a single recipe for what it should be, but I can give you some of the things that I think matter a lot for programming in Scala, and that are often overlooked by, if you look at the fancier things like macros and monads and higher kind of types and so on. So far, when I've given a Scala talk, I've always had this picture to say, well, Scala is a unifier. It's a scalable language that is both agile with a lightweight syntax, and you can scale it up to very, very large systems indeed. So Twitter has, are you allowed to say how many lines of code are in production in Twitter? Person from Twitter here. Last I heard it was more than 4 million, something like that. Okay, so the meaning of scalable, if you look at this, to say, well, a scalable language, what does that mean? Then it really has 2 meanings. The first meaning would be it's a language that can be grown. And if you don't really have a good idea what that is, I really recommend you look up that talk by Guy Steele. The talk is called Growing a Language, and it was given at UPSLA 1998, which gives you the best impression, not only for the brain, but also for the heart of what growing a language is. So growing a language then means, on a language term, that you want to start out with a simple vocabulary of language concepts, and then you want to grow it by adding libraries, and the libraries should sort of make the code look like it was written to the base language. So I can give you an example of a language that's definitely not growable in that context, and that would be Go. Go is a language which is a very strong language in many respects, but it's not growable because it gives you a fixed set of abstractions, channels, sequences, arrays, and they are privileged. They can be parameterized with other types, and that's something that you cannot do for things that you might want to design. So the level on which the user program is written, the vocabulary available to the user program is closed. You can't really add new words, new meanings to it, at least not using generic types. And that was a very good, very conscious decision, so I'm not criticizing Go for that, because there are very good reasons why sometimes you do not want to be growable. So growable is, as we're going to see, actually has its own challenge. The second meaning, I'm going to come to that later. So growable language, it definitely is. Scala definitely is one. What makes it growable? What makes it a language that can grow into new domain-specific domains? So it has a very flexible syntax. It has a very flexible type system. There are user-definable operators that are often used with abandon by many communities. It has powerful control flow combinators using higher order functions. It has implicits. It has a very rich toolbox for essentially constructing your own domain-specific languages. And that has happened a lot. So a lot of DSLs have sprung up. Here are just some of them. So you've seen Spark. So Spark is essentially an extension of Scala, but the extension is done as a library. So Spark has defined essentially its own library abstractions, and they give you essentially the power of queries, SQL-like power in queries. So that's a DSL on top of it. Or Spray for HTTP dispatch, or Shapeless and Scala Z for type wizardry, or Slick, another front end for databases, Squirrel, then the test framework, Scala test specs, the akka, the actor framework, dispatch, SPT. SPT, the build tool you interact, is also nothing more than a DSL that sits on top of Scala, at least the Scala part of SPT. There's one which is sort of very, very thin syntactic sugar on top of it. If you have a .spt file, then essentially there's a pre-parsing step. But by rights, it's really a DSL on top of it. Okay, so growable. So isn't that great to be growable? Shouldn't we all say, well, everybody should do Scala and Go, they got it wrong, it's not a growable language? Well, actually, it's a challenge. So another growable language definitely is Lisp. It's so growable that people sometimes say that Lisp is not a language, it's essentially a meta language for writing languages. Everybody can write a language in Lisp. And that's, of course, a lot of people love Lisp precisely for the thing, but there's also a very good paper called the Lisp Curse. So the Lisp Curse argued that it's very hard to essentially get anything large off the ground in Lisp, because it's so ridiculously easy to write your own little DSL. And because it's so easy, everybody does it, and nobody finishes it. If you want to start a project, let's say in C, to write your own high-level library for doing X, then you will know, well, it will probably, to get started, you'll need several person years to do that. So you better organize yourself. You have a large team, the community comes together, and you do this, bring this thing to the end. In Lisp, that hardly ever happens, because a single person can do it in an afternoon. I'm exaggerating now a little bit, but it is like that. And because everybody can do it, everybody does it from scratch, and the community fragments. So fragmentation is a big issue with being too growable. The other issue is that, of course, once you have all these DSLs, then not everybody likes each other's DSL. For domain-specific languages, that's the same problem as for general-purpose programming languages. People have tastes. They like one language much better than the other, and the same holds for the domain-specific languages. So that also can lead to some of these fights. So some of the fights we have in the Scala community is that some people like the domain-specific language Scala Z, to pick a word, much better than other people. So they disagree about the usefulness of Scala Z, and that's of course a disagreement that you can have. That is essentially, you can disagree about every language that you discuss here. Okay, so Growable is great for experimentation, for growing initially, but there are challenges for large-scale production use, and you have to use a lot of conformity and discipline for that. Oops. Good. The other meaning of Scalable means enabling growth. So that means you can start with a small system, you can start maybe with some experimentation in the REPL or in a worksheet, and you can grow from there and take it all the way to a really large mission-critical system. And Scala is also pretty good at that. So you can experiment, you can grow without fearing to fall off the cliff, you can grow very large indeed. So that works because the language has abstractions that are essentially scalable in the sense that you can start small, but they hold up for large programs. They're enough abstraction power to make large programs hang together very well. So for the language, that works very well. I know very well that the tools are sometimes challenged. Build times comes to mind, but I think they're catching up. So I guess the challenge is a continuous challenge, that because as the tools are catching up, of course, the code bases get larger. So you always have to sort of stay ahead of that. But I have some trust in the current Scala compiler team that they will stay on top. And I think the latest releases with the faster incremental compiler in SPT, that was already a big progress here. But I'm not denying that more progress needs to be made. Okay, good. So what enables growth in Scala? So ultimately, I believe it's this combination of object-oriented and functional, this peculiar mixture between object-oriented and functional that stands up there. Unfortunately, there's no established term for this. People say we do functional programming, or they say we do object-oriented programming, and then these say I hate you, or these say I hate you. So that's typically what what happens. So if you say you're both functional and object-oriented, then they both say I hate you because you're you're the other side. So so these are sort of finger-pointing arrows here. So to escape that curse, I think it's good to actually think about, can we find another name for what this is, this mixture of object-oriented and functional? So some people have called it object-functional, but I don't really like names with hyphens and slashes in them. It reminds me too much of PL1. So what I would propose is to call it a modular language. And that's really old-fashioned, because old modular languages, that was like Stone Age of computing, but I sort of proposed to go back to that term. So what does modular mean? So modular means that a modular system is a system that's composed of modules, obviously. And what is a module? Well, a module should be a simple part that can be combined in many ways to give interesting results. So a good image of a module is, let's say, a Lego brick. You have Lego here in Japan for the kids, for the little children? Lego, yeah. So a Lego brick is something very simple. At least it used to be. Now they're very complicated, some of them. But it used to be very simple. But you can build very interesting things with Lego bricks because they're universally combinable. So that's sort of what a module should be. A simple thing, and that can be combined in flexible ways. And simple usually means encapsulates one functionality. Who here has seen the talk by Rich Hickey, Simple and Easy? So some of them have. So Rich argues the same things. Essentially, simple means one functionality. Don't mix functionalities in a thing. You could say, well, that's really old hat. Should we all go back to Modular 2? That actually wasn't so bad a language. My first compiler was in Modular 2, and I was very fond of Modular 2 at the time when it was popular. That was like the early 80s. Shows you how old I am. But of course we shouldn't. So Modular 2 was, I think, a very good modular language for its time, the early 80s. But nowadays it would be completely outdated because it's really part of these von Neumann languages, and it hits the same von Neumann bottleneck. So what I mean by that is that the von Neumann languages, of which, let's say, probably C and C++ are the latest exemplars, they are languages that are very close to a computer. So they model a computer directly in the language. So for instance, the variables of your language, there would be memory cells in your the computer's memory. Control instructions would be jumps, and that would be it, basically. And the problem there is to pass to a larger scale. If you talk about something much bigger, like a text string or a web page or things like that, they don't really fit into a single memory cell anymore. They're very complicated structures, and they can't really be represented directly with these von Neumann languages, because essentially you have to represent it by peeking and poking a lot of memory cells, and then you invariably have the problem, how do you manage memory, who is responsible for deallocating this memory that you have allocated here, and so on. So you're on the wrong level of abstraction. And Modular 2 was a language in the same category, which was in the early 80s, I think, the only one that worked, because computers weren't that big that you could usually have the luxury of abstracting a whole lot from the actual hardware on which you were running. So in today's systems, we have much richer models and implementations. And one important, I think, influence for modular programming is functional programming. So another very important paper, well, I should go back, I haven't said that. This guy here, that's John Backus, and he's very interesting, or he was, he's deceased. John Backus was the inventor of Fortran, which was the first high-level language, very much a von Neumann language, an imperative procedural language. And in the 70s, he got the Turing Award, which is sort of the Nobel Prize for computer science. And by the time he got the Turing Award, he gave a speech which said essentially what we did in Fortran was good for the time, but we should get away from this model because he coined this term, the von Neumann bottleneck. And this bottleneck is essentially the buzz, which means that I can access memory only one word at a time. I can't treat structures as a whole. I have to peek and poke single variables. So that was him. And the other very important paper, I believe, is from John Hughes. The paper is called Why Functional Programming Matters. It's a very short paper, easy to read. Don't know, who has read this paper already, who's come across? Some people here, yeah. If not, then if you have some time, look it up. It's a worthwhile read. So the paper essentially argues that functional programming is good because it leads to parts that can be combined very freely. So what they try in the paper is that they give you essentially a algorithm. The algorithm they pick was for computing square roots. If you've seen my course on Coursera, then you've seen that basically the same problem very early on in the course. And it shows the same thing with a loop which mixes many concerns. It mixes the iteration step and the termination criterion and the how to deal with rounding errors all in one loop. And then it says, well, if you want to split these things into different modules that we can combine from the outside, there wouldn't be lines in the loop. There would be things functions that we can combine from the outside. That leads to functional programming. So you could argue that this paper here, which was sort of the foundation of functional programming, I would say, in fact, argued that functional programming is modular programming, that it's very good for that. Okay, so is functional and modular programming then the same thing? Are there synonyms? I think actually not, because at least if you go out and look at common concepts in functional programming, then some of them are very good for modularity and others are not really. So just one example that I give you here is in Haskell you have type classes, and type classes are a very powerful and beautiful feature, and Scala has something very similar with implicit parameters, but they're not modular, because the thing that makes them not modular is that for a given type class you can have only a type can only have a single implementation. So that essentially fixes it for the whole program. In a sense, it's similar to monkey patching in Ruby, where you say, I add this method to this class and I do it for the whole system, for the whole program. So if somebody wants to add the same method to the class, but with a different functionality, then you will have crosstalk and bad things will happen. In Haskell it's much better behaved because it's statically typed, but still you can't have two different implementations of the same type class with the same type. And that means that let's say the type class is, I don't know, comparisons of strings, and in one part of the program, of your program, you have a certain string ordering, and in another part you want to use a different one, then sorry, you can't use a type class for that. You have to all agree on one. And that's something that sometimes is worth doing. It also has advantages to do that, but it also has disadvantages, and that's precisely the loss of modularity here. Okay. So object-oriented languages, they are in a sense the successor of the classical modular languages, because in classical modules essentially what you wanted to say is that you want to have multiple implementation. So a module has an implementation and an interface, and then you say, well, you want essentially to get rid of this one-to-one correspondence. You want to have multiple implementations of the same interface, and a single implementation should have multiple interfaces. And that essentially both of these generalizations led to object-oriented programming. So you could say it's sort of modular programming on steroids, but it's not functional, so it misses that part. And again, object-oriented programming, there are also some practices in some languages which are not really modular. So for instance, I already mentioned monkey patching, then another one would be mutable state is actually not very modular, because it lets you have very long, far distance effects. So you change this variable here, and over there sometimes you need to respect or know that this variable was changed. And of course we all know that sort of the further apart or the more global your state is, the more complexity you will get. Okay, so I'm come now to the language, and maybe I won't have time to discuss library modules anymore, but I want to start with the simple parts in the language itself. And one way to express them is that they correspond directly to fundamental actions that every programmer does during programming, and that together, I believe, cover the essence of programming in Scala. So the actions that you're going to see is composing, matching, grouping, recursing, abstracting, aggregating, and mutating at the end. And as always, simple is not easy. I come back to this talk by Rich Hickey. So that means, what I mean by simple is, does one concept and does it well? No different difficult things to set up or things like that. Easy, by contrast, that means that's something I know already. It's familiar to me. And it looks easy because it's familiar. So something might look very difficult for you, but it might in the end be very simple, but it's just something that you haven't really learned yet, or that you haven't really been exposed to yet. That's the big difference between simple and easy, and I'm argue simplicity. So the first thing that is often overlooked, but I think it's really important, it's the expression-oriented nature of functional languages in general and Scala in particular. So what I mean by that is that everything that you write is an expression. And that's good because that means everything else can be plugged into everything else. Everything gives you a value that can be plugged into the next expression. So a simple example is that this if expression, if age greater or equal 18, grown up, else minor. In Java, you would have to write either a thing with question mark and colon, which nobody does because nobody remembers the syntax, or, of course, more commonly, you would write a statement. You set a variable to grown up, or you set a variable to minor. But that means once you have a statement, you have something that is not easily combinable with other things. You have to arrange them in a sequence. You have to be careful that the side effects happen in the right order, and so on. Here's another one, of course, in Scala for a match, the generalization of switch. Again, it's an expression, it's not a statement. And the same thing holds for try as well, so for exception handling. So everything is an expression, and that means everything can be combined with each other. The second thing is that where expressions can compose data, pattern matching can reverse that process. So it's the dual of building expressions. Instead of composing expressions, it decomposes expressions. And in Scala, pattern matching is written in a way that really drives that home, because essentially a pattern looks exactly like an expression, only it appears on the left-hand side of the arrow. So essentially, left-hand side of the arrow decompose, right-hand side of the arrow compose. So here's a simple pattern match, which I guess everybody here can read. You have the space straight expression with two cases, numbers and plus. And here a match of whether it's a number n, then I give you back the number, and when it's a plus, I go into a recursive evaluation of this function. So it's very simple, it's very flexible. Sometimes it's a bit verbose, but I don't think that's a major concern. The shortest is not often simplest and clearest. The reason for the verbosity here, so a lot of people have said, well, why is it so verbose? Why do you have these case classes and not something like an algebraic data type, like in Haskell, or I think Swift now will have algebraic data types for these things. So the reason really was simplicity, to say, well, we don't really want to have different ideas of types for different usages. We want to have a single thing for types, and that means every type is a class, and our only sort of distinction is subclassing. We have that already in an object-oriented language, so we can use it for pattern matching and case classes as well. And that gives you for free nice things like you can seal that trait, and then you have a finite number of cases, and the compiler will check that you used all of them. But you can also not use sealed, and that means you can have essentially an open sum of cases, and that's also sometimes very, very important. So if you look at functional languages like Haskell and ML, what they have is they have these algebraic data types. But one thing that doesn't fit this model is exceptions, because exceptions is something where you want to sort of add new ones. You don't know, you don't have a sum of things that you know from the start. So people come up with new exceptions all the time, and there should be sort of a nested hierarchy. So for instance, file not found is a subtype of IO exception, as we know in Java. And that means that these languages then need another concept for exceptions. And often it goes that far that in order to get an open sum for something else, which these languages then often don't have, people actually misuse exceptions because that's the only way to get an open sum for these things. So you see that in Scala, despite the fact that this thing is a little bit more verbose, you get essentially a lot of freedom for composition on the other hand. So that's sort of the trade-off here. Okay, I'll probably skip that. Good. So the third thing is grouping. So one thing that again comes from functional languages and I think is important is that everything can be grouped and nested. So typical languages like in the C and Java tradition, they are flat. So C, you have essentially every function is by itself. You can't put one function into another. In Java, every function, every method is a part of a class. You can't put a method inside a method. Even though what you can do is you can put a class inside a method and then the other method inside the class. So that works, but you can't put a method directly inside a method. So the nesting thing means that you have complete freedom to put your things into the closest scope where they should go. And the other thing it means, it encourages you to find names for new things. For instance, here we have a method solutions where we say I want to have a stream of a path, so all the possible solutions, and I get essentially I call a function all paths, and I want to filter it with something that decides whether this thing is a solution. So where something is a solution says the path, the last state of the path should contain my target state. Okay, so in traditional imperative languages, there would be a very, very strong trend push to writing a loop where this thing just gets mashed up in the loop. Why? Well, you could pull it out, but if you pull it out, then you have essentially a global method or a class global method, and that method might not make much sense. Furthermore, that method then would have to be parameterized by target because it refers to target, and target is not visible here. So if you do that, then you tend to come up with a solution which sort of pulls the program state inside out. So the program state is sort of visible in the method parameters in these methods. And that's why often people don't do it. So that's why often you get much, much larger methods, many more lines that essentially mix many concepts, which basically is the opposite of modularity. So the fact that we can have local names means that it makes it much, much easier to use these names. And that's something that I really would very much recommend that you do. In fact, when I'm asked essentially what is good Scala style, how can I improve my Scala style, my answer typically is the first one, the most helpful one is to say, write your program that on every line you define something meaningful. And that meaningful thing that you define, you should give it a name that reflects what you have defined. So have a good readable name on every line of your program, no matter how you achieve that, no matter what you use. If your program is like that, then it probably will be fairly readable. So the opposite of that is something that I saw once in the Scala code base. I think it was in the IDE somewhere. So that's essentially a long expression, and of course you're all Scala experts, right? So you can read this and tell me what it does immediately. Well, there's a filter and a flat map and a flatten and oops, yep, all mashed into one. So it's amazing what you can get done in a single statement, but that doesn't mean you have to do it. So I tried then to sort of refactor this. It's the same logic, but I just tried to come up with meaningful names. So it seems like after deciphering what this thing does, we define something which is sort of the sources of my IDE, of my program workspace, and there's a workspace root that I have here, and then I have I use essentially an anonymous method which also deserves a name, namely the files corresponding to an entry, and then at the end essentially I have just I go through my sources and I do a flat map with files of entry, and that's what happens here. So you see that by the simple thing of just saying find a meaningful name for every line of the program, you have achieved a lot. And that's something that often takes time because in the end, if you're an expert, it actually, oops, sorry. No, let's go again. I have to learn how to use this properly. Okay. In the end, if you're an expert, then often it's actually faster than to just flat map, things like that, and you have it. But whereas the other thing, we have to think hard. What am I going to define here? But it's something. It's an investment that is very, very well spent, I think. Okay. So we have seen what have we seen so far? We have seen the expression composition. Everything is an expression. We can decompose them with pattern matching. We can group them with local scopes. Number 4 for me would be recursion. So recursion is something that is a bit weird. Often people jump more or less directly from loop-based imperative programming to sort of the higher order thing with map, flat map, and filter. And I think often that's exactly the right thing to do, to say, because map, flat map, and filter, they're really very, very easy to use, and they are powerful combinators, and somebody else has debugged them for you. So if your problem fits into that mold, that you can express it as something like a collection or a monad, and you can run these functions over it, then definitely that's a very good thing to do. But there's then a gap between these two worlds. I know my loops, I know my combinators, map, flat map, filter. What if my program doesn't fit between the two? And then people often do acrobatics to say, well, maybe if I have a flat map over a group by, and then I do this other thing, and of course you can achieve everything by every technique. In the end, everything here is Turing complete, but often it's a game of diminishing returns. And that's when I quite often reach to something which is far, far simpler and say, well, let's just use good old recursion, and often paired with pattern matching. Here it isn't. I probably would have used pattern matching for this thing, to just say, okay, let's recurse over something, pick something, pattern match on it to give me the cases. For each case, essentially have my result, and often the result then recurses over the original thing. So what's also important is that there's no performance tax here. If you have a lot of higher order operations, then if you have large collections, then they often get amortized. But if you use them on small things, like you do a lot of flat maps and folds and maps on, let's say, option types, then that's okay for some cases. But if that thing is performance critical, which of course you should check with a profiler before optimizing, but if it is performance critical, then these things are gonna cost you. I promise you that, because there's a lot of boxing and unboxing involved, and all these higher order functions, they don't come for free. Whereas what this thing does is it translates directly into an imperative loop, so it can run just as fast as a Java while loop over the same thing. There's no performance penalty whatsoever on this thing. So if something has to be fast, and or if the logic is sort of involved and doesn't really fit your combinators, then this is a great fallback. And I find myself writing less and less loops. I hardly ever write a loop anymore, so if you asked me, can Scala do without the while loop and the do loop? I said, yes, tomorrow we can throw them out, because I always fall back to this. I never fall back to a loop anymore, basically. That's sort of my thing. Again, it's not the shortest often. You have to write a certain things. You have to write these names, but defining names is good documentation. It's actually, it actually makes the program quite readable. Good. Number 5 are abstraction. So functions are abstracted expressions. So an expression is something that you compute, a computation. And now when you say, well, I want to sort of name this computation and make it more general by giving it parameters, then of course you get a function. And in functional languages, functions are themselves values. And we all love that, of course. That's a great thing to have. And it's also great that they can be both named and anonymous, but don't overdo the anonymous too much. So I think the anonymous is fine if you have like a simple expression like that, but if it gets multiple lines, then please do write a function, give it a name, and then pass the named function instead. That's something that I think Python has probably done quite well, because in Python you have only the named functions, and there's something called lambdas, but I think it's almost unofficial, or it's deprecated, or very much discouraged. So in Python you always have to write essentially a local function before you can pass it back to some other things. And often that's the more legible thing of the two. Good. Number 6 then is aggregate. So aggregate is done with collections. So collections aggregate data, and of course that's the functional paradigm. So where the imperative paradigm is CRUD, create, read, update, delete. You don't really tend to do that. What you tend to do instead is you take a collection, and then you have a uniform set of operations that give you a new collection at the end in a functional way. And whether you do that on in the REPL with a simple array of 3 elements, or you do that with Spark on a cluster of several hundred nodes, it's the same operations and it's the same idea. That's the power of these collection operations here. So the number of operations that collections have, or I should say that the Scala collection library has, these are all library functions, is quite large. So it takes some learning to know them all, or to know most of them. But it has the advantage that then it's universally reusable. So you can, essentially you can apply these collections, these operations for all sorts of collections in the Scala library, whether it's a linked list or an array or a vector or a map or a set. It's always the same collections. And if you go to like distributed collections like Spark, then they have a slightly different implementation and meaning, because most of them are lazy on Spark, but it's again the same name. So when you see the name, you know immediately what it is. So that's a very good thing. And what I wanted to do here is defend a little bit some of the attacks that have come towards collections, who said, well, take a step back. I think all of you using Scala collections have the impression that it seems to work pretty well. It seems to do what I mean. I just type it and it comes back. But some people actually object and say, well, no, they are not pure enough. They have all the wrong types. So one commonly found objection is that the type of map is either ugly or a lie. So let's look that up. So here, if you look it up at the Scala doc, you see, let's say for the array data type, you find the map function, and it gives you a function from A to B and an array of B, given an array of A. So that looks good enough, but there's this use case underneath, and of course if you are fluent in Scala documentation, you know that use case, something hides behind the use case. So let's look what hides behind the use case. Okay, so here's the full signature. There comes a nice explanation what it does, but then comes the full signature, which says, well, actually what map takes is not 1 type parameter, but 2. And then there's this implicit BF can build from one to the other. So people object and say, well, that's a very, very complicated type to remember and to keep in mind. So my answer to that would be, if all you do is mapping functions over arrays or lists or sets or whatever, so you're a user of these collections, then that's the type that matters. The rest is completely under the cover. You won't ever see that. This type matters only if you want to write a collection with its own implementation of map, which is generally a very, very bad thing to do, because this general map, will actually be the map for all collections, whatever, if you define certain much simpler functions right, namely a function to just come up with a builder for the collection. So that type essentially means even if you write collections or if you use collections, you don't want to touch that type. You don't need that type. It's sort of analogous to a dynamically typed language where something complicated happens when it treats your collections to sort of give you back the same collection type you started with and things like that. People don't open up the Clojure interpreter and say, oh, this is very complicated code. Clojure must be a horribly complicated language. They don't do that, right? And this is exactly the same thing. This is internal code, which is there, so that we can have a single map for all collections that matter, and that's something very, very important. I can tell you what we did before. Before we did the absolute standard thing to do. We had every collection had their own collection operations, a map, filter, and things like that. And their types were all really simple, like that. There was one for array and one for list and so on. But what then happened, it's around the 2007 time frame, is that people started to use different methods on different collections because the implementers of these collections differed. And that means users were constantly surprised to say, why is this thing called append here and concat over there, and things like that. So that's why we sort of said, well, we need to design things in the right way that we can have one map for all collections. Okay, you could say, well, yeah, good, but why did you pick that type? Why not that type here, a functor? So you have a functor and you say map should, it's a part of the functor type class. It takes a function from t to u and a functor of t and gives you back a functor of u. Well, that doesn't work for arrays, unfortunately, because for arrays actually to create a new array of u, you need a class tag. The JVM doesn't let you do that, to just create a generic array where you don't know the type, because the JVM needs to know that the type to store in an array, because essentially arrays were the JVM's or Java's broken attempt to do generics in 1.0, and that's why these arrays all have these essentially type tags in there to prevent storage errors. So don't get me started. It's a horrible, horrible story that haunts Java until this very day, that these seemingly innocuous arrays, they really pollute everything. Everybody who touches them has a problem here. So arrays require a class tag, and therefore you can't do map. But the arrays are actually not that unique. That is the case in any case where we need some additional information. For instance, if you want to build, have a map function from sets, ordered sets to ordered sets, then you need an ordering to be able to find that. Or if you would be strict with your equality to even do a simple set, you'd need an equality function because sets don't have duplicates. And that means there are many situations where when you build a collection, you need some piece of extra information, whether it's an ordering function or a class tag, or you want to restrict the type, as for bit sets or strings, it's all the same thing. And all these purposes essentially are fulfilled by can build from. So that's why it is the way it is. Okay, good. So let me just finish up with the last point, mutate. So I would say the last thing that Scala has, and for good reason, is it does have variables, and so it has mutable state. And you should be very careful using it, but one should not deny that Scala has mutable state, and one should not stay away from it forever. One should just have to use mutable state. One should have a good reason, but there are good reasons to use mutable state. Well, one objection, of course, would be I talk about modularity. Aren't variables anti-modular? And in fact, they are. If you use global state, that often leads to hidden dependencies. But when you use them widely, a mutable state can actually cut down on boilerplate and increase both efficiency and clarity. So let's see what I mean by that. So in the compiler I'm currently writing, I'm sort of on a journey to write an almost purely functional compiler, which the current Scala one is not. Another compiler that has made this transition into a pretty functional compiler is the C# compiler. That's Project Roslyn, on which they have been working for the last 5 years or so. So that new compiler has now become the standard compiler for C#, and it's written in a pretty functional style. So in a functional compiler, you have a lot of challenges for clarity and also speed, because of course speed matters for compilers. We all, everybody here would like the Scala compiler to become faster, right? So when we do functional programming, we have to ask ourselves, well, wouldn't that hurt the efficiency too much? And in fact, for the Scala compiler, it's the other way around. We don't have any efficiency to lose. We have to gain a lot of efficiency. So can we use these techniques to gain efficiency? And at first it seems weird because functional programming is very abstract. It's far removed from the computer. So how can you gain efficiency? What leverage could you have where functional programming helps you to gain efficiency? Well, one thing that helps you to helps in efficiency is caching. So the compiler has a lot of computations, which it does all the time. And some of these computations are duplicated. So sometimes, for instance, if I want to look at what is the member of this complicated type with this name, that might be something that I have already computed before, because it's quite often that I essentially select the same identifier. Or I want to say which implicit conversion is applicable for this type. Again, that's something that if it's something common like just adding some stuff to string or to int or to collections, that's something that probably happens a lot in my program. Even in single sources, it happens repeatedly. And if I have a build of a large code base, then probably there are hundreds and thousands of places where I do the same thing. So if I can cache this thing, I could gain potentially a lot of speed. So caching is a thing where mutable state comes in a lot, because caching has to be done smartly. So it's a science by itself, how to cache well, how to cache cleverly, and it's not something that you can just put into something that is pre-configured. So of course you could say Scala has a caching mechanism built right into the language. It's called a lazy val. So that means I compute it only once. The second time somebody needs it, I have the value. But it's far too limited, because it sometimes hangs on too long to the entry. It doesn't work for functions. It doesn't work for arguments, and so on. So we do a lot of caching in different ways in this compiler, using memorized functions, interned names. We even use LRU caches, because sometimes we can't do a full cache because it gets too big. So we have a very, very fast LRU cache for the member selection that I mentioned, where essentially the last 8 names that I selected on a given type are stored. And older hits are evicted as this thing gets full. Persisting, that's another thing. So persisting is the idea that you have compute things, and you typically compute them in maps. So you say, well, for every symbol I have to compute this property. So this can be expressed as a property from symbols to something. You compute a map. But then when you're done with the map, you want to essentially say, well, now I don't want to keep the map around, because A, that's a potential space leak, unless I make it a weak map, and B, it is too inefficient, and weak maps are even more inefficient than normal maps. So what I want to do, the fastest way to do, is to just store this value in the object when I've computed it. And that, of course, I can only do when the object doesn't change anymore afterwards, because otherwise it wouldn't be purely functional. But if that value gets computed exactly once, and it will never change afterwards, I might as well store it in the object. And there are several other techniques like copy and write, fresh values. So that's another thing that is not strictly functional, but we often think that, of course, you want to do that. So for instance, a fresh name generator that you say every time you call it, it gives you a new name, just a name with a number that gets incremented, these sort of things. That's things where you say, well, that's mutable state, but it's mutable state that you use, which doesn't really break your modularity or your program, but it makes it clearer in the end, and it makes it also much more efficient. So once I've done all this thing, all the caching and persisting, copy and write uses state cleverly. So it uses state in the implementation, but it's still a purely functional interface. So for the outside, this thing is purely functional, but because it uses state, it's fast. Once I do all that, I'm actually left with 2 mutable state variables that I have to thread through the whole compiler, basically everywhere. So they are the current constraint and the current diagnostics. So the current constraint is an object that gives you essentially the subtyping constraint for the inference. It tells you what type must be a subtype of what other type when you compute type variables. So type parameters, best solutions, and things like that. So that's number 1. And this number 2 is compilers, of course, produce errors or diagnostics. And again, because there's a certain backtracking involved, sometimes you don't want to spill that out immediately on the console, because that might be just one branch that the compiler tries, and there might be another fallback branch. So we keep that, we buffer that internally. In fact, we buffer it lazily. We don't even compute it unless we spit it out on the console. That's the current diagnostic. Okay, so, and those are 2 global variables in the compiler. Well, variable trees, they're versioned in the compiler. So the one question here is, well, shouldn't you use a monad for these 2 variables? Their state, right? And purely functional thinking should use a state. So you could, but it's not necessarily a win here, I would say. So because here you have two typical functions in that compiler. First function is a function typed. It takes a syntax tree that's called untyped tree and an expected type and gives you back a typed tree. So that's my type checking function. And I have a lot of them for different forms of trees and things like that. And another function which is quite typical of what I do is the subtype function, which says, well, is this type a subtype of that other type? So that's this extends or conforms relationship. Okay, so if we put it into a monad, let's call it typer state, and it contains the error log and the constraint, then of course these things would be different. I would have written type takes the same parameters, but now it doesn't give me back a tree. It gives me back a typer state of tree, which is a tree wrapped together with the current constraints and the current error log. And a subtype, the same thing. It would have to give me a typer state of Boolean. Okay, so you could say a bit more clumsy to write, but explicit, and explicit is good. So explicit definitely is almost always good. But let's look at the usages of these types now. So instead of now, so we would write something like this. So some condition which says, well, T1 must be a subtype of T2 and T2 of T3, and then we can give you back a result. I would now have to write something like this. I would have to write a for comprehension or a flat map over a monad to do that thing to say, well, let's compute this thing and pull out the Boolean value into C1. That's a Boolean, that's a condition. Do the same thing in C2, ask whether C1 and C2 both hold, and yield the result. And I'd have to be very careful to actually keep the lazy behavior here, that I have to pick my monad very well, that is subtype is actually not computed if the first one is false. But there are ways to do that. But then you ask yourself, well, which one is better? And the answer is, well, it depends. If really it's a big issue that you care about the state and you want to have it in everybody's face, maybe you should write things like that. But if you have an implicit contract which says, well, a compiler needs a constraint and an error log, and everybody knows that, and every function needs that, then I would argue, yes, definitely, this is much, much better. It's shorter, it's clearer, it abstracts from the things that you don't want to see in your face. So I'm a bit iconoclastic here. I go up against the functional dogma, which probably, at least if it's the functional dogma is, well, no, I shouldn't say functional dogma because it's really functional statically typed Haskell dogma, this thing here. If you talk to a Clojure guy, you say you must be crazy to write something like that. Of course you would write it like that because we hide these variables in a lot of other things. We hide them from you and you don't do that. But in Haskell you would have to write it like that. So I go up a little bit against that. And but you can rest assured that at heart I'm a functional guy, because I believe what matters in this whole exercise, what matters is this, to be left with two variables. So to do this minimization and to say all the other interfaces, we essentially distill down to say we don't have any extraneous state until we arrive at sort of the essence of what we want to keep around everywhere. And once we're there, we can put it in a monad or not, and people might disagree about that. But the functional part, the functional exercise is to arrive here. So don't get too hung up about it if you use functional programming without the monadic abstractions. It's still functional programming and might be just as good as the other, or sometimes more appropriate. Okay, so to finish this talk, I just maybe finish with this slide here to say, so I argued about modularity and functional programming, and there's this other angle which is essentially type correctness. And they get often mixed, the two. That type correctness and functional programming in some communities get mixed up a lot. And I think it's important to disentangle these two properties, to say the question how much you want to capture in your type system is very orthogonal to the question of whether you're functional or not. So for instance, if I take Clojure, then there is no static type system. Well, there is a statically typed Clojure, but I don't think many people use it. Most people would just use the Clojure compiler to check the syntax, and that's it. Scala is more traditional in the type system. You check the types of the arguments and the results of functions. In Haskell, you go one step further. You also check the types of effects. So by putting variables into monads and not giving you direct access to effects. And it doesn't end here. You could then go to Idris, where you essentially talk about precisely what values get returned, and you can express properties like an even number or an array index that's in a given range and so on. And then if that's not enough for you, you can always, there's always Coq and Isabelle and theorem provers like that, which let you essentially prove the correctness of something. And once you've done that, it often doesn't matter anymore whether you have a program or not. So you have all these, this big spectrum where essentially none of these 5 approaches is right. It's really a question of trade-offs and where you want to be. And I think different people have different preferences where they want to be. Whether you want to say, well, types get in the way, or types are very helpful, or we also want to check effects because that's great, or to go further to dependent typing and full correctness are all valid decisions that you might want to take depending on what kind of software you're tasked to write. Okay, so to conclude, from the fundamental actions to simple parts, what we've covered is what I think are sort of the essence is an expression-oriented language that has good scoping facilities, that lets you decompose expressions with paramatching, that has functional abstraction, a function value and recursion, that has a powerful collections, and the fallback to use mutable vars. That's what I think is the essence of Scala. So but that's sort of the core of it, and my ambition is to show you that this essence, if you take it as that, is actually something that's rather simple. Thank you.
Thank you very much, Professor Odersky. So, is there any questions? 何かご質問ありませんか?
So thank you for your talk. I have a question regarding .c, actually, and another question about OCaml. The question about .c is, so we know that so far the JVM has been trouble. I mean, since the Scala has primarily targeted the JVM, there are limitations due to that. So I wonder for .c, so if So I wonder if for .c you make more an abstraction of a JVM targeting more general, more like a general compiler, like for instance, in which the JVM itself would be just one target, and maybe like JavaScript would be another target, and then do some glue code for the JVM, or if oppositely to that, the JVM would still be the main target. And the other question is, so regarding OCaml, if you could just describe what you didn't have the time to do before, please. Thank you.
Okay, so first the new compiler project, which is called .c, so dot is the calculus, C is short for compiler. So the transformation pipeline to Java is not quite finished yet, but what we've done so far is pretty close to what's there before. So some of the things change, in particular also because the JVM has changed. So it now has lambdas, and we can use lambdas directly. We don't have to write anonymous inner classes anymore. And those changes also profit alternative backends such as JavaScript, because the current Scala JS compiler is hampered by the fact that essentially we generate these anonymous classes from the start, and then anonymous classes can be translated to JavaScript. That's not a big deal, but it's not as lightweight as only generating a function. So whereas now that we sort of keep functions in the pipeline until the very back end, we can then essentially have alternative ways to map it into Java and JavaScript. So in certain things are will get better. There are other things where unfortunately we're still very, very much tied to Java, and there's nothing we can do. So I guess one of the biggest complications for the compiler is really the overloading, that Java has overloaded methods, and the overloading is very liberal. You can have many different methods from many different base classes that you can inherit. You have complete freedom to overload that, and that makes enormous problems for compiler writers. Of course, it's very convenient for users. So if you ask users, then they say, yeah, overloading, great. And if you ask language designers or compiler writers, for the first thing they want to remove, they all say overloading, away with it. But it's something that, so that's something we unfortunately are stuck with. And that's a bit irksome because JavaScript doesn't have overloading. So if it was for JavaScript, you wouldn't have to do that. But since we still have Java as the compilation target, we have to sort of put a lot of restrictions. So there are things like, there are things like these restrictions that you say for the overloaded variants that you have, they must have different erasures. And that's sort of where the JVM comes out to say, hey, first there's this erasure concept, and secondly there's the overloading concept, and that gives you a certain limitation of what methods you can do. And that's sort of something that we need to have because we run on the JVM, but for a JavaScript backend this is sort of weird because that gives you fairly arbitrary restrictions of what kind of methods you would write. But yeah, that's the reality and we have to live in it. For OCaml, you mean the modularity aspect? Or yeah, so what I meant by that, but I didn't want to go into details really. What I meant by that is if you write a variant or a record field and you don't use the module system, so you don't use qualified names, but just simple names, then you have the same restriction that you can't use the same fields in two different records. And that's something that a Java programmer would find weird. They say, I write two different classes and they can't both have a name field, you must be joking. But in OCaml you have this restriction, but it's a bit, it's not as harsh as it sounds because you can get around it with the module system. Yeah. But then you have to qualify all your names. You have to really put a prefix, a module name dot prefix everywhere. Yeah.
Thank you very much. So it's a kind. So I thank you very much for Professor Odersky.
Thank you.
And 拍手でお送りください。